Welcome back. Recall that in the last class we were discussing linearization process and linear stability analysis of nonlinear systems. So, let me just recall what we are doing. So, this was our autonomous system and x bar and isolated. Okay. So, that is standing assumption. Equilibrium point, and then the linearized system is given by y dot equal to d f x bar y, and this is the Jacobian of the vector f at x bar. So, it is an n by n matrix. Okay. So, when we analyze this one, we called it linear stability analysis of this nonlinear problem. So, we are doing examples. So, let me again recall that Duffing's equation or it is also called Duffing oscillator. So, after some simplification we reduce the equation with many parameters to only one parameter. So, and this is second order equation x double dot. So, second order equation. So, x is a real valued function, x dot plus or minus x plus x cube plus delta x dot is equal to 0, delta is positive. So, let me just concentrate on the negative sign, and the positive sign is similar. In fact, there is only one equilibrium point in that case. So, let me write that negative sign as a system. So, this is x dot equal to y and y dot equal to, if I take negative sign. So, this is x minus x cube minus delta y. So, the equilibrium points. So, if you compute, so the first equation gives you y equal to 0, and so this is from first equation, and second equation then implies that x into 1 or minus x square equal to 0 or x equal to 0 plus or minus 1. So, therefore, in this case we have 3 equilibrium points 0 0 plus or minus 1 0 are the equilibrium points. And now, let us calculate the Jacobian at these 3 points. So, let me just calculate the general the Jacobian at a general point x y. So, if you, this is the now 2 by 2 matrix, we are just in a 2 dimensional system. So, if you take the first function, so I differentiate with respect. So, first again go back. So, if you go back, so you see that the first equation contains only y and second equation is x minus x cube minus delta y, So, this will be 0 1 1 minus 3x square minus delta. Okay. So, at 0 0, let us calculate the Jacobian. So, df 0 0. So, this is just 0 1 1 minus delta. Okay. So, the eigenvalues you can compute them are half minus delta plus or minus square root of delta square plus 4. Okay, you see that for all delta non-negative, the eigenvalues are real and are of opposite signs. So, one is positive and one is negative. So, we conclude that from the linear stability analysis. Okay. So, we invoke all the linear theory here. So, 0 0 is unstable. Okay. In this case, we also call it a saddle point. When the eigenvalues are real and of opposite sign, the unstable equilibrium point is called a saddle point. And at plus or minus 1, since the Jacobian has x square term, so it is same. So, df plus or minus 1 0 is just 0 1. Now, it is minus 2 and minus 10. 1 minus 3x square. So, that gives us minus 2. So, the eigenvalues here easily computable, 2 by 2 matrix. So, no problem. Eigenvalues are half again minus delta plus or minus delta square minus 8. Okay. So, this in case of 0 0, you see that it is plus 4 and here it is minus 8, and that makes a difference. Okay. So, so for all delta positive, for all delta positive, the eigenvalues have negative real part. Either they themselves are negative real numbers or certainly they have negative real parts. So, therefore, plus or minus 1 0 are asymptotically stable, linearly asymptotically stable. When delta is positive. So, what happens when delta is 0? When delta is 0, the eigenvalues are plus or minus root 2 I. So, therefore, plus or minus in that case is okay, both are same, are linearly stable, but not asymptotically stable, because here the real parts are 0, they are purely imaginary. So, this is again from the linear theory when delta is 0. Okay. So, delta equal to 0 also false this case. In this case, the equation itself is in conservative form, and we will study these things a little later in detail. So, at that time again I will recall this. So, when delta equal to 0, the equation is referred to as undamped unforced Duffing equation. Okay. Duffing equation also referred that, if you recall, that nonlinear term x cube is referred to as cubic stiffness term, and that is used to describe the hardening spring effect observed in many mechanical systems. Okay. So, this is to describe the hardening spring effect observed in many mechanical systems. Okay. So, with this we move to the next example. So, this is another important equation that is studied extensively, and it has also given rise to new mathematics in the theory of nonlinear dynamics. So, this is called van der Pol equation, or again oscillator. So, van der Pol in the years around 1927, when he was working for the Philips company in Netherlands, extensively studied this equation both theoretically as well as experimentally using electrical circuits. Okay. So, this is one of the, again this is a second order equation. So, given by x double dot plus mu x square minus 1 x dot plus x is equal to 0. So, this is unforced. Okay. So, there have been many studies even with periodic forcing term. I will give some reference. So, when mu is 0, you see that this term vanishes and you get back our simple harmonic oscillator. So, when mu is equal to 0, this leads to linear harmonic oscillator, simple harmonic oscillator. So, this nonlinear term is added to that, and see whether you still get periodic solutions. Okay, when mu equal to 0, certainly we have periodic solutions, and would like to see whether mu non equal to 0 also produces periodic solutions. Okay. So, you can imagine, okay, so when mu is negative, so that is interesting case. So, we will do the linear stability analysis for this also. When mu is less than 0 and x is small, So, this if you compare with the spring mass dashpot system, so this is the damping term, but this is non-linear damping. So, this is non-linear damping. So, in spring mass dashpot system, this was a constant, but here we have this non-linear, this coefficient depends on the solution itself. So, in the engineering parlance, this is called the oscillator is driven when x is small. We will see what that means mathematically, and damped or slowed down when x is large. Okay. So, when x is small means this x square minus 1 is negative and I have mu negative. So, this whole thing will become positive, and that will produce exponential terms with positive terms. Okay. So, that is, so there are large oscillations, but when x square is bigger than 1, then with mu negative this also becomes negative, and that acts as damping, and the oscillations will be slowed down. So, effectively what we expect is, in this case, so we expect this figure. So, we see that we will check that 0 0 is the only equilibrium point in this case, whatever may be mu. So, this when you start the solution near 0, so it just moves around and try to approach a periodic solution. Okay, so, let me just take, so this is the periodic solution, and again when you start from far off, that also try to come and approach this, and we will see later that this is the case. All solutions starting at the different point than the equilibrium point, all approach a periodic solution, and that is indicated as a red circle here, not circle, but some closed orbit. Okay, we will see that later. So, let us do the linear stability analysis. Very simple here. No, I am not restricting mu to be negative. Analysis. So, these two examples are important for us, Duffing equation and van der Pol equation. So, again write as a system. So, x dot equal to y and y dot equal to minus mu x square minus 1, x dot is y, and I have minus x. Okay. So, 0, if you solve again the right hand side equal to 0. So, first equation gives me y equal to 0, and if I put that in the second equation, that gives me x equal to 0, whatever may be mu. 0 0 is the only equilibrium point. So, hence isolated. So, even in the previous case they are all isolated equilibrium points. So, 0 0 with the only, and if I calculate the Jacobian, that is again simple here, d of 0 0, and this is again 0 1 minus 1 mu. Okay. So, the eigenvalues are given by 1 by 2 mu plus or minus mu square minus 4. Okay. So, you see that when mu is positive, so the so this always dominates, and so you will have, so both the eigenvalues have positive real parts. So, hence unstable. Okay. So, mu equal to 0, the equation itself is linear, the equation is linear, and it is 0 0 is stable, but not asymptotic. Stable. And mu less than 0. So, the real parts are negative, and hence 0 0 is asymptotically stable. So, as I said in the beginning, mu is positive, that is the interesting case, and we will see that little later. Okay. So, let me now describe a situation when the linear stability analysis implies the nonlinear stability. So, that means, if linear system is stable, then the nonlinear system is also stable, and if linear system is unstable, then the nonlinear system is also unstable, and this goes by the name Hartmann-Grobman theorem. Okay. I just explain this only in English. Okay. I will not even write down the precise terminology, I just explain with only words. Okay. So, the situation is x bar is a hyperbolic equilibrium point. So, last time we defined this. So, let me again recall what that means is this d f x, the Jacobian of f at x bar. So, this is a matrix has eigenvalues with has eigenvalues all having non-zero real parts. So, this is important, non-zero real parts. So, in this context, when x is a hyperbolic, x bar is an hyperbolic equilibrium point, the Hartmann-Grobman theorem says that. So, you have this nonlinear system and you have the linearized system. Okay. So, you just work here orbits around x bar, okay, the orbits, okay. And here also you, this is 0 and you take orbits of this linear system here, and then to compare these two. So, you just add x bar here, okay, and the orbits here. So, orbits around x bar and orbits around 0 of this linearized system, add x bar to that. So, they are linked by a homeomorphism. Okay. So, it is an interesting and important theorem. Locally it describes around a hyperbolic equilibrium point. So, the orbits of the nonlinear system can be gotten from the linear system and vice versa. So, this is an important result, and this happens only around a hyperbolic. A somewhat simpler one and older than this Hartmann-Grobman theorem, referred to as Perron's theorem. Though it is not as precise as the Hartmann-Grobman theorem, it gives us some sufficient conditions again for comparison of nonlinear systems, orbits of nonlinear systems and linearized system. So, let me state this and give a proof. Though it is technical, since we have developed all the technicalities in the linear algebra portion, it is very easy to give a proof of this. So, let me just state this. Okay. So, we have this system, a linear system perturbed by a nonlinear. So, this f is different. So, this is a system. So, the hypothesis on A. So, A has eigenvalues all with negative real parts. So, Hartmann-Grobman theorem requires the eigenvalues all to have non-zero real parts, but here the Perron's theorem, it only concerns about the eigenvalues when they all have negative real parts. Okay. And f is a continuous function. Okay. Let me not bother about where it is defined, but it will be defined in a neighborhood of 0, and this is important hypothesis, and this indicates smallness. Okay. So, this is little o of mod x as mod x tends to 0. So, uniformly in T. Okay. I will clarify this little later. So, what does this mean is this limit mod f T x mod x tends to 0 is 0 uniformly in T. Okay. So, that means this limit process does not depend on T, that is uniformity. Okay. So, the usual epsilon deltas that appear in the definition of this limit, they do not depend on t. So, that is what meant by this uniformly in t. Okay. Then the 0 solution. Zero solution is asymptotically stable. So, again read the definition of asymptotic stability carefully. Stable for star. Okay, so let me put this star. So, that means if I start a solution of star near the origin, but not at the origin, because origin is always a solution. Okay. I would like to show that the solution exists for all time and the solution tends to 0 as t goes to infinity. Okay. There are two steps. Okay. So, proof. Let me just indicate a proof of this, and in our case when we want to apply to the linear stability analysis, f t x does not depend on, this is just a quadratic in x. So, it does not depend on t. So, automatically this condition is satisfied. So, there is no problem. So, the Perron theorem implies that 0 is asymptotically stable when the linearized problem has the matrix, the Jacobian matrix in the linearized problem has eigenvalues all with negative real part. So, let me just give a proof of this. So, you see some interplay between analysis and linear algebra and differential equations, of course. So, proof of Perron's theorem. So, the local existence theorem local in time theorem implies. So, whatever may be my x 0, so given x 0 there exists a solution x t. So, let me indicate that x t of star with x 0, okay, that is for some time t in 0 t star. So, t star is positive. Okay. So, that is always guaranteed. What we would like to do now is we want to show that when this x 0 is small, that the solution can be extended to all t positive, that is the first step. Okay. And once we show that thing, we are not interested in weakness here, that is why there are no hypotheses on little f in star. So, so this is by Peano existence theorem that there is always a solution. So, there are two steps. Okay. So, claim if x 0 is small. So, remember this is the standard Euclidean norm. So, this x 0 is a vector in R n. So, if this is sufficiently small, then x t can be continued. So, this is also part of the existence theory we have done earlier. When is it possible to continue a solution which exists for a short time to all times, continued for all t positive. Okay. And then, so this is 1, and then limit x t as t tends to infinity equal to 0. So, both these things prove the result. So, 1 and 2 will prove imply the theorem. Okay. And let me just stress as a remark, this is not trivial. So, remark, okay, 1 is not trivial. So, it does not follow automatically. Okay. So, we already seen an example where the solution does not exist for all time. Okay. So, for example, x dot equal to x square. Okay. So, no matter what x 0 is, if x 0 is positive, however small it is, okay, that does not matter, the solution exists, solution x t, okay, exists only in 0, 1 by x 0. We have already seen that. Okay. Of course, this does not, this equation does not fall under star, because there is a linear term here. So, the linear term is 0 here. Okay. So, that is that A part, the hypothesis on the eigenvalues of A plays a crucial role in order to prove claim 1. Okay. For example, so if I want to compare this example with star, so I take x dot equal to minus mu x plus x square, and I take now mu positive. So, this falls, this is similar to star equation in 1D. Okay. Then you can, as an exercise, check that x, the solution x t exists for all t non-negative, provided, okay. So, this is the smallness what we say in the theorem, provided 0 x 0 is less than. Okay. So, once you exceed x 0 bigger than mu, you can also check that the solution does not exist for all time. Okay. So, that is crucial. Okay. So, remark 1, this claim 1 is not trivial. Okay. So, this remark explains that. Okay. So, now we want to exploit the hypothesis on A, namely the eigenvalues of A all have negative real part, in order to show that the solution exists for all time. Okay. The local solution, which I know exists for short time, that 0 t star x t satisfies. So, this again you recall, we have proved the existence by converting the given differential equation into an integral equation, and I am going to write the same thing. Okay. x t satisfies the relation equation x t is equal to e to the t a x 0. This comes from the homogeneous part x dot equal to a x, and then for the inhomogeneous part you have this nonlinear integral e t minus s a f of s x s t s. Okay. So, again remember this t is only for short. Okay. So, whenever that x t is a solution of the differential equation, it can always be written in this. Okay. And one more remark here, it is remarkable that the same technique works even for infinite dimensional systems, where the matrix A will be replaced by a differential operator with good spectral properties. What are the good spectral properties? Like here the matrix A has all the eigenvalues with negative real part, and similar to that, if you assume the same process without any change even works for infinite dimensional systems. So, this is a powerful technique. Okay. The methodology in Perron's theorem, the proof of Perron's theorem is a powerful technique which is used even in other situations. Okay. So, now the hypothesis. So, let us by hypothesis. So, in the previous thing, that e to the t a is the exponential matrix which we have defined in the linear algebra portion, and I am going to use some more properties from that linear algebra. So, by the hypothesis on A, so this will show in detail in linear algebra portion. It follows that so e to the t a okay. So, this is matrix norm which we have introduced in the linear algebra part. So, this is less than or equal to some constant, positive constant k e to the minus sigma t for some k positive and sigma positive. This is important. The sigma positive, let me just briefly explain where do these two constants come from. So, this essentially comes from the Jordan canonical form which we have already discussed in linear algebra portion. So, when we use the Jordan canonical form of A, so this constant k is produced, and sigma comes from the eigenvalues. So, sigma is essentially okay, half you can put any fraction there. So, minimum of minus of real of lambda eigenvalue. And you see that is where so this is spectral property of A. So, eigenvalues describe the spectrum. So, this comes from the knowledge of the eigenvalues of A, and by our hypothesis this minus real part of lambda are all positive, and I am just taking there are only finitely many eigenvalues and they are all this real part is now minus real part is positive. So, this sigma is positive. So, half you can replace by any fraction. So, that is no problem. Okay. So, this is a very crucial step in the proof of Perron's theorem. So, this estimate is very crucial, and this we have done in linear algebra. Okay. Once we have this thing, now I invoke the hypothesis I want to now write it in terms of epsilon and delta. So, given epsilon positive, there exists delta positive such that whenever mod x less than or equal to delta, we have f of t x is less than or equal to epsilon by k. So, this is for technical reason that k I am already using it, mod x uniformly in T. So, just this means again, as I said earlier, this delta does not depend on T. So, this does not depend on T. So, when f itself is independent of T, so that uniformly in T does not arise, but when T is there, so we want this delta to be independent of T, so that we can just concentrate only on the x variable. Okay. So, now let me call this as 1 and this as 2. Okay. So, these two estimates play a crucial role. So, again go back to this. So, remember this solution satisfy this integral equation 0 to t as e to the t minus a s a and f of s x s ds. So, this implies, so remember this value is only for a short t. Okay. Our aim is to extend this to for all t. So, taking norm and using estimate 1. So, this gives me minus sigma t x 0. So, this is Euclidean norm plus 0 to t e to the minus sigma t minus s and this f of ts. And now, I want to use the hypothesis on f, and for that I require only, say if I want to use that estimate 2 on this thing, I require that mod x t is less than or equal to delta, and that I assume that for the time being, and I will show that. Okay. So, this is less than or equal to epsilon by k x s provided norm x t is less than or equal to delta for 0. I will show that. Okay. So, if you now put all these things together in this inequality, so what I get is e to the sigma t. So, I take that this side, this less than or equal to. So, there is a k here, there is a k here. So, that is k x 0. So, this k cancels. So, I have that just. So, I take that e to the sigma t other side. So, what I am left is just e to the sigma s, there is an epsilon here, mod x s t s. So, provided this, okay, again I, so this is valid provided that. But now look at this inequality. So, concentrate on this function. The same function appears on the left hand side and this in integral, and this is the situation where we can apply the Gronwall's inequality. So, so this is also we have already seen the importance of Gronwall's inequality in proving uniqueness inequality. We have e to the sigma t x t is less than or equal to k x 0 e to the epsilon t. Okay. So, that epsilon comes there. Okay. So, if we choose now, if 0 less than epsilon less than sigma, then we have x t less than or equal to minus sigma minus epsilon t, and now this with assumption on epsilon, and this is just k x 0. Okay. So, this is the crucial inequality we have obtained, provided, see all these things you have to remember that all these things are derived provided x t is less than or equal to delta. So, we have to somehow now assure that x t will be remain less than or equal to delta. Okay. And now that is easy. So, now the hypothesis comes into picture. So, therefore, if mod x 0 is less than or equal to delta by k. Okay. So, this is the smallness assumption that is indicated in the theorem. Then, if you look at the previous inequality for all 0. So, indeed the solution has remained less than or equal to delta. So, all the steps we have derived are legitimate and they are valid. So, hence the solution. So, this is the bound, okay. The solution x t can be continued. So, that means it exists continued for all t, okay. And this is the smallness assumption. Okay. So, remember those, this is just independent of. So, they are just come from essentially on the hypothesis of little f and on the matrix A. Okay. And then we also have this k x 0 e to the minus sigma minus epsilon t. So, we have already chosen that epsilon is less than sigma. So, that goes to 0 as t goes to infinity. Okay. So, thus we have proved both our claims 1 and 2, and that completes the proof of the Perron's theorem. So, what we have learnt? What we have learnt? So, so this the hypothesis in Perron's theorem is also a hypothesis on the equilibrium point x bar. So, A will be d f x bar, okay. So, it all has negative real part, the eigenvalues have negative real part. So, in case of, so this is the, in case of hyperbolic equilibrium points, so this is important. The linear stability implies stability analysis implies nonlinear stability. So, if the equilibrium point is hyperbolic, then the linear stability analysis will be sufficient to conclude the non-linear stability analysis, and linear stability analysis is much easier as we, because we have explicit formulas and other things. So, the only case that will be left out is the case that is left out is that of non-hyperbolic equilibrium points. So, that means the Jacobian matrix now will have eigenvalues with 0 real part, and that we have seen through examples that the linear stability analysis may or may not imply the non-linear stability. We have seen example where in case of non-hyperbolic equilibrium points, the equilibrium point may be stable in the linear linearization, but unstable or even asymptotically stable in non-linear case. Okay. And this one is more effectively handled by the Lyapunov function, and that will be the topic of our next discussion, next class. So, the Hartmann-Grobman theorem and the Perron's theorem take care of the case of hyperbolic equilibrium points, and the non-hyperbolic equilibrium point case will be handled by Lyapunov functions. Okay. Thank you.